If you're making a battery-powered project which might even use multiple lithium-ion cells in series, and the idea of using a BMS has ever crossed your mind, you might have noticed that the ones you can buy suck, since they've all sacrificed performance and size to save an extra 50 cents per unit, which becomes especially noticeable if you're wanting to push even medium currents. And the DIY circuits from some of these YouTubers don't help either. I mean, GreatScott uses this massive DIY system meant for literal home power walls, and ElectroNOOBS circuit
may, in my personal opinion, have limitations when it comes to designing a BMS safely.
And I know what you guys might be thinking. What could this small YouTuber possibly show me to prove that he isn't full of it and not just trying to confuse us all for views and profit? What about 3 18650 batteries protected by my custom BMS development board, dumping the power of 9 laptops charging at the same time into this heater for not a few seconds, but more than a minute, and not even getting close to thermal limits? I know all those things together makes no sense. That's close to 55 amps per 18650, and for a whole minute? You're joking. And the actual BMS part of my development board is only 40 by 40 millimeters. You can see it in the thermal view. The rest of the board is just completely unrelated functions. But this is what happens when you do months of research and optimize every single component to prioritize safety first, which gives you the leeway to play around with some absolutely insane power density. So hang on, let me explain what's going on here. There's only one correct way to make a BMS, and if you disagree, drop in the comments down below why. And that is, the response from the BMS when one or more voltage, current, or temperature limits is exceeded is that it should manipulate the main power path to indefinitely guarantee that the given limit isn't further exceeded. After we're back into the safe range plus a set value called hysteresis, which stops the circuit from bouncing in and out of the fault response, the power path is free to return to normal. Except for short circuit, which it follows would require a power cycle to clear instead. The easiest and most space-saving way to do this is by using a fully integrated BMS chip, which reads the voltage of each cell as well as the temperature and current of the pack, responding by driving the gates of the power path MOSFETs, all in a single package, which is what my development board implements using the BQ77915. There are some other ways to do this too though. Some AliExpress development boards repurpose 1S protection and balance ICs and cleverly jerry-rig the signals for any number of cells in series, which reduces costs but increases board size significantly. And it doesn't help that the FETs they use are honestly rubbish. I mean, you'd need 15 of these in parallel to achieve the same low resistance as just one of these. And if you break it down further, I've made some example analog circuits which I'd assume would be pretty close to what's going on inside these BMS chips, for over voltage, over current, and over temperature in charge. Even though no one really does this because it increases costs and board size when done right, so unless you're using like a rare lithium-ion chemistry with a weird voltage range, there's no reason to. I'll still go ahead and explain what's going on in the voltage monitoring section because this is the part where everyone seems to get confused. Using resistor dividers to monitor the voltage of a multi-cell pack is generally avoided, not only because we lose most of our signal range and the resistor tolerances add inaccuracy and drain the cells at different rates over time, but also the fact that you wouldn't be measuring cell N's voltage, you'd be measuring cell N's voltage plus cell N minus 1 and so on. Which is extremely annoying to deal with unless you're using a microcontroller, and even then, still extremely annoying to deal with and less accurate than the solution that I'm about to show you. Instead, you get a difference amplifier like the INA149, I have a great video link below which explains difference amplifiers, but basically what this does is it takes the cell voltage signal and shifts it down to a ground reference. That's most of the problem out of the way there. After that, it's fairly simple. If any cell voltages are above the overvoltage threshold, it'll set the latch so that the charge FET will be disabled until every cell reaches below the overvoltage threshold, minus hysteresis, at which point the latch will reset and the charge FET is free to turn back on if no other faults are detected. Feel free to ask questions or make criticisms about these circuits in the comments. You can pause here, here, or here if you want to analyze this circuit and let me know what you think. On the other end of the spectrum, you also have programmable BMS chips, which are highly configurable but seem to be a pain in the GAT to develop with. So I've never tried.
One way to implement protection features that can be more risky though, in my opinion, is by using the DIY circuits GreatScott and ElectroNOOBS show us, because those circuits just waste power from cells which exceed the overvoltage cutoff, which could be dangerous if the cells are far enough out of balance and the charger is fast enough since the design doesn't actually disconnect them.
Of course, we can't forget about balancing, which, although it's generally not considered to be a part of the protection system and more of a nice to have so that the cells share the load and degrade as equally as possible, is still usually included in most BMSs in the form of passive balancing, which converts the extra energy from the higher state of charge cells into heat, with active balancing generally being reserved for the higher end commercial BMSs and larger lithium-ion packs, using capacitors or inductors to transfer energy from higher to lower cells instead of wasting excess energy. This is a whole other topic within itself though, so I'm not going to go into too much detail in this video. I do in fact have a big project coming up which will use capacitive active balancing and some of those protection circuits I showed you earlier, so make sure to stay tuned for that and subscribe. Anyways, back to the main question, what is it that truly separates my board from some of the AliExpress BMSs and allows it to handle this much power in such a small space? Well, PCBWay's high quality PCB and PCB assembly services allowed me to select these 0.34 milliohm FETs from their wide range of electronic component distributor partners and double the thickness of the copper in the PCB. So if you want the same performance and quality in your own PCB projects, click the first link in the description to create an account at PCBWay and get $5 off your first order. This month, Purple Solder Mask is at no additional cost and there are massive discounts on 3D printed TPU parts above 20 grams, so I'd highly recommend checking them out. Let's get back to the rest of the video. Of course, my BMS isn't here to just sit there and look pretty. So here's some protection tests with the omission of overcurrent, since I don't even have anything that'll draw that much power, short circuit since that needs a power cycle to recover, which I can't even do with the way I soldered this wire, and under temperature, since I'm Australian. With the BMS side of things out of the way, there's still half of the story to explain though. What about the battery pack? How on earth is that handling what? 53 amps for more than a minute and not even getting close to thermal limits? Well, these are no ordinary battery cells. They're Ampace JP30s, the best performing 18650 on the planet when it comes to power, and they put the cells you're used to absolute shame. Without a solid spot welder to make the interconnections between the cells ready for high current operation though, these battery cells may as well be useless, but luckily for us, A/Z has got our back with the P30C. A supercapacitor spot welder which can output 24 kilowatts and weld 0.2mm thick copper for the most high performance battery builds. You ready?
Yep.
Alright. Thanks to A/Z for this great piece of equipment, and if you want one for yourself, click the card or the link in the description. In my next video, I'll be running some more fun tests with my inverter here, so make sure to subscribe for that. I'm again putting the manufacturer part numbers of the main components I used in this BMS on screen, as well as literature which will help you make something similar to what you saw in this video. But if you don't want to design your own board and you want to see a product like this released except it's only the BMS, comment down below what I can improve, watch this video again to see if there's anything you missed, and hit those buttons. Thanks.